So, we will continue with our lectures on simulators. In the last lecture, I had introduced two different types of simulation techniques. One is known as the event driven simulation and the other is the cycle based simulation. So, just to recapitulate that the main difference between these two is that given a combinational circuit, okay, you can have many gates in that circuit, and what the event driven simulation does is that whenever there is a change in the input of any of these gates, then we only simulate those parts of the logic which are affected by that. So, what happens is, suppose there is a input change in one of the gates, then we just propagate it along the output of that gate and see what are the fan outs of that gate, and then again take those gates, schedule events on them, okay, and we continue in this way until the circuit reaches a steady state. Right. Now, the good thing about this is that even if the circuit has a loop, a combinational loop, you can still keep on scheduling the events until the circuit stabilizes. Now, if the circuit does not stabilize, then obviously this simulation will continue, and at some point of time we will have to decide that this circuit is oscillating, and therefore, we will never end the simulation by reaching a steady state. Okay. On the other hand, the other approach, which is called cycle based simulation, there we actually look upon the circuit as some combinational logic and a set of flops, and we know that the output of this combinational logic will feed into the flops, and the flop outputs in turn will go back to the combinational logic, and there can be some more primary inputs. Right. Now, given this view of the circuit, we know that the values that will be latched on the flop are not going to happen at any point of time, but at certain edges of the clock. So, we are basically interested in computing the values at these points just before the edge of that clock, okay, because that is the value that is going to be latched. So, in other words, we just need the steady state values, the values that arrive at the inputs of the flops after the combinational logic has stabilized. So, if that is what we want, then we do not really need to schedule all the internal events, we just need to wait for all the inputs to stabilize at the cycle, and then after it has stabilized, then we just compute what are the values of the outputs. Right. And by this approach, every gate of the combinational logic is simulated exactly once in every clock cycle. Right. Whereas, in this one, it is quite possible that some intermediate gate is simulated many number of times, because some input changes here and it ripples through this path, then another input changes here and it again ripples through this. So, this gate might be simulated many number of times. So, this is essentially the difference. Then after that, we were looking at approaches to perform the event driven simulation. How does the event driven simulator work? So, there we were looking at the notion of a timing wheel or an event manager. So, essentially every event driven simulator goes through the following steps, that it first it has a list of events. So, the basic structure is like this, that there is a list of events, and this list of events is sorted on time. Sorted on time. Now, when what we do is we take out events from this, right, then execute those events, which in turn generates new events, with timestamps, and then these events are again pushed back into the event queue. right, and these events are sorted on time. So, you might see that for one value of time t there can be one set of events, then for another value of some t plus delta there is some another set of events, okay, and so on. Now, this in turn is represented by what is called a timing wheel. So, this is the timing wheel. So, these events are sorted on time. Now, the important thing to note here is that within the events in a given time there can again be an order in which the events are executed. So, like we have the blocking, non-blocking, okay, the triggered events. So, within the same time, the same unit of time, there can be many events and there might be an order between those events imposed by the semantics of the language which is being simulated, right. So, as I said just now that within the scheduling semantics in Verilog, at a given simulation time are stratified into 5 layers of events in the following order of processing. And apart from these future events which are going to take place in the later clock cycles, which in turn are again divided into different time buckets, these 4 events are executed, these 4 types of events are executed strictly in this order: active followed by inactive. Inactive, by inactive remember that we mean the events which are preceded by a hash delay or hash 0 delay rather, because they are all in the same time. So, it is only for hash 0 delay, and then we have the non-blocking assignments and the monitor statement, and monitor is basically to observe the output of the circuit. So, that happens at the end when everything is stabilized, right. So, now let us look at the 2 types of events that are generated by the simulator. Now, what I mean is that for every event when we come to the execution, so at this step when we come to the execution, this execution actually produces 2 things. One is that it can generate an update event or an evaluation event, right. There is a difference between these 2. So, let us study what is the difference between these 2 types of events. When an event is placed in a queue, it only means that the event may happen, right. I will explain why it is the case. It just says that it may happen. Whether it actually will happen has to be evaluated. Why do we say that it may happen? Because we are saying that that event will happen sometime in the future, right. Now, in the intermediate period from the current time up to that future time, it is possible that there are other events which will happen, and as a result of the other events that event will have no effect. Okay. So, we are going to see examples of this kind of situation. So, just because we have an event in the queue, it does not mean that it is finally going to affect anything. It may not actually affect anything. An update event occurs when a variable or a node changes its values. So, that is called an update. Okay. Any change in the value of a variable or a node. When an update event has occurred, all processes sensitive to the variable or node are triggered and must be evaluated. That is fair enough, that whenever some signal changes, you look at the fan out of that signal and then you schedule an evaluation event for all of them. Okay. Now, this evaluation process is called an evaluation event. So, it evaluates the logic of that gate and sees whether any changes are going to take place or not. If an evaluation event changes the values of some variables, then update events are generated for the affected variables. Okay. So, if we see by evaluating that logic that its output is going to change or may change in the if nothing else happens in between, then we will schedule an update event, say that this output of this gate will become 1 after so much amount of time, right. So, update event simply replace the existing value of a variable or node with the new value. So, when that update event is finally executed, it just replaces the old value of that variable with the new value, right. Let us see an example. So, this is a single gate AND gate with two inputs A and B. The delay from A to C is 3 nanoseconds and the delay from B to C is 1 nanosecond, right. At time 1, this B has input 1. So, at time 1 we have 1 here, and input A has a rising transition. So, at that time input A rises from 0 to 1. Now, when one input is 1 and the output rises from 0 to 1, the output of this gate is going to change from 0 to 1, right. So, this triggers an now whenever this A rises, it triggers an evaluation event for the AND gate. Why? Because the input A was updated, which was this rising transition, which is actually an update event. That updation affects the variable A, and this is in the fan out of A. So, this has to be evaluated. So, the evaluation event for the AND gate does what? It checks the logic of this and sees that this is 1, this has now become 1, C was originally 0. So, it schedules an update event which says that change C from 0 to 1, and what is the timestamp of that? The timestamp is after 3 nanoseconds. So, if this is time 1, then it is going to get scheduled at time 4, okay, 1 plus 3. So, this is the update event that is scheduled. Now, let us see what happens. At time 2, this B input falls at time 2, right, and the delay from B to C is 1 nanosecond. So, we first schedule an evaluation event for this gate. That evaluation event finds out that after 1 nanosecond, the output of this is going to be 0, right. Now, note one thing is that this was 0 at time t equal to 3, this was 0, right. So, what happens is that even though see this is not really updating this variable anymore, but it does set this to 0. Okay. So, let us see what we interpret this as. Since delay from B to C is 1, a future event T 2 for output C at time 3 is scheduled. Okay. Now, when time advances to 3, we evaluate E 2, we evaluate this gate and conclude that output C is 0, right. And at time 4, when we evaluate E 1, the first event, we show that C remains at 0. So, the event is suppressed or cancelled. Now, note two very important things here. The first thing is that at time t equal to 1, when we realize that this output could change, we cannot really say that it will change. We again will have to evaluate the value of C when we are sitting at time t equal to 4, right, because in the intermediate period some other gate may have changed, and then that may have actually forced this value to stay at 0 and it will not rise, all right. So, the question therefore rises is that at a given time t, if I have to evaluate the output of a particular gate, what will be my algorithm for doing that, right. I know I cannot do it at the time when the event was triggered, because if I schedule the update at that time, that update may not actually take place. Like for example, here the event E 1 is suppressed or cancelled, it does not actually raise the value of C. Okay. So, this is the algorithm. Let the present time be t, G has n inputs and the functionality of the gate G be f. Okay. For each input xi of g, let the value of xi at time t minus di be yi, where di is the delay from xi to the output of g. Right. So, for example, when I want to evaluate the value of c at time t, I will look at the value of a at time t minus 3, okay, and I will look at this one at time t minus 1, right. Now, if you look at the previous example, if you remember the previous example, B had fallen at time t equal to 2, right, and therefore, that lowered the value of C at time t equal to 3. Okay. Now, so if I look at time t minus 1 out here, so this was t was 4 here, right. So, we were evaluating C at time 4. So, t minus 1 was 3. So, at time 3 this value was 0, because B had already fallen at that time, right. So, therefore, this value we are taking as 0, and this value we are taking as 1. But then if in an AND gate any input is 0, then the output is 0. So, at t equal to 4 C evaluates to 0, which is what we are expecting. Is that clear? So, now let us see what is the event scheduler doing. It is only scheduling that at time t equal to t plus delta, you have to evaluate that gate, right. If at that time the evaluation changes the value, then we generate an update event which will update the output of the gate, and the outcome of that update event is not only just to update that gate, but to put the schedule the next set of events which are in the fan out of that signal, to schedule events for evaluating them at the appropriate times. Clear? So, this is the event propagation methodology. When an event has been confirmed to happen, all fan out gates or blocks sensitive to the event must be examined for event propagation. It is dangerous to delete a future event at the current simulation time when it appears not to happen in the future, right. Now, to give you an example, just the opposite of what we did could also happen. So, here is our AND gate, this is 0, right, and this one rises, all right. Let us say this has time 3 nanosecond as before, right. So, we compute this and find that we have this rise transition. So, we find that this becomes 1, this becomes 0, and then we might say that okay, since one input of the AND gate is 0, so do not schedule any event here at time t plus 3. We might say that, because it does not appear that the output of the gate will change. So, the evaluation event at time t plus 3, given that this takes place at time t, if we do not schedule that, then there can be a problem. What problem? Is that at time t equal to t plus 1, at that time this one might rise, and this might have a 1 nanosecond delay from this to this. So, after 1 nanosecond, this output will still not rise, because that output is still at, that 0 has not, the 1 has not yet propagated, right. So, the output will still show 0, but at time t plus 3, if we evaluate it, then at that time the value of this at 3 nanosecond previously has risen here already, and this one has already risen 1 nanosecond previously. So, at t plus 3 if we evaluate this gate, we should get 1, right, and we will miss this if we had not scheduled the evaluation event when we updated this rise event, right. So, even though at that point of time it appears that the output will not change, you still have to schedule the evaluation event, right. So, that is actually in a way it is a bad news. Why? Because you have to keep on propagating your events and you cannot filter it out by looking at the present values of the inputs. You still have to propagate it, because in the meantime your other inputs can change and they can change faster, resulting in some updation when that event is finally taken up. The other interesting thing that we need to see is that fan outs can change during simulation time. So, it is possible that something that we, so I have one block, and then this block is the signal that we have here, let us say A, is being used in 2 other blocks, right. Now, you might be tempted to feel that whenever A changes, I need to evaluate both of these, because they are in the fan out of A, right. But what I am saying here is that it may so happen that at some point of time this block is sensitive to changes in A, at some other point of time the same block may not be sensitive to A, which means that the fan out of A can change at different points of time. How can that happen? So, that can happen in a case like this. So, this is an example. So, I have 2 gates, gate A produces the output x, gate B produces the output y, and then we have this always block where we have the following thing: at x we do some A equal to B, and then at y we do B equal to C. Now, remember that this is a block which is going to execute in this sequence, right. This sequence is important. So, what is this block going to do? It is going to wait for a change in x, then assign A equal to B, and then wait for a change in y, and then assign B equal to C. So, now when the block is waiting here, not here exactly, just excuse me, yeah, when the block is waiting here at this at x, at that time it is not sensitive to the changes in y. See, as long as x is not changing, even if y changes, there is this always block is not going to get evaluated. Okay. This always block will be evaluated only when x changes. Then after x changes, then it will do this assignment and then come and block here in at y. Now, when it is waiting here, at that time if x changes, it does not care, that is not going to schedule this block anymore, right. Only when y changes again it will get scheduled. So, you see the same always block will sometimes be in the fan out of gate A and will sometimes be in the fan out of gate B, right. So, dynamically the simulator will have to maintain this information. It has to also maintain the information that at which point in the always block is the current control, and therefore, what is it blocked on. Okay. If it is blocked on x, then it is in the fan out of gate A. If it is blocked on y, then it is in the fan out of gate B. Right. So, you can imagine that simulator has to do a lot of housekeeping all the time to maintain these kinds of information. Otherwise, you will end up simulating the block many number of times. All right, that is not incorrect, but that is inefficient. Then time advancement. When do we advance time? When no event for the current simulation time remains, the simulation time is advanced. if a maximum number of iterations is exceeded without time advancement, the simulator declares that an oscillation has occurred. Right. This is the criterion for terminating when your circuit is not stabilizing. There is a combinational loop and it keeps on scheduling events and does not terminate. I mean, there can be some more ideas on this by looking at the structure of the circuit, etc., but broadly this is the philosophy of what is done. So, now let us come to the event driven scheduling algorithm. I think we already know most of it. So, this is a simulation cycle for an event driven simulator, and this is not just restricted to hardware simulation. This is a generic algorithm for all event driven simulations. While there are no events, if no events are there for the current time, so as long as there are events, we will loop in this while loop. If no events are there for the current time, then advanced simulation time. And then for each event at the current time, remove the event from the event queue and process as follows. If event is update, then update the variables or nodes and schedule evaluation events for the affected processes. So, this is what we understood by the update events, that they update the variables values and then schedules the evaluation of all the affected processes. Affected processes means those that are in the current fan out of that. Otherwise, evaluate the process if it is a evaluation event and schedule update events for outputs that change. Right. Now, these now see, this evaluation is actually looking back in time and finding out whether anything is at all going to change. If it does change, then it schedules the update events for the outputs that change. Right. So, that is all that we had to discuss about event driven simulations. Now, we will proceed to cycle based simulations. Do you have any questions on event driven simulation as such? Okay. So, let us move to cycle based simulators, and then we will look at some hybrid techniques between the event driven and cycle simulators. In a sequential circuit, every time the flip flops change, many events are generated in the combinational logic, but only the steady state is latched at the next clock edge. So, evaluations of all the intermediate events are wasted, because in the end it is only the steady state value that is going to get latched. Cycle based simulators evaluate the combinational logic at each clock boundary. They just look at the clock boundaries. Each gate is evaluated once in each cycle, and the important requirement is that the circuit must have clearly defined clocks and their associated boundaries. Right. The clock has to be identified. Now, we need to, the first thing that we need to do in order to do a cycle based simulation is a thing called levelization. So, we know that we want to evaluate every gate only once. Right. Now, look at this case. In a particular cycle, these are the things that have happened, that the output of this flip flop has changed from 0 to 1. The output of this flip flop has changed from 1 to 0. This input has remained at 1, this input has changed from 0 to 1. Right. Now, we assume that all of these take place at the same time, because we are only interested in the steady state values. So, at this, when every input has stabilized, these are the values which matter, the value 1, 1, 1 and 0. Right. In event driven simulator, what would we have done? We would only look at the ones which have changed and then schedule output events there. Now, see, if you follow that kind of principle, what might happen is that you may first schedule the gate A that causes a change in input here, because A this input of A was 1, it remains at 1, this was 0. So, it has risen to 1. So, the output was 0, it has changed to 1. Now, when it changes to 1, at that time, see this B will also change, because as soon as one of the inputs, previously both of these were 0. So, the output of this, in other words, B was 1, right. Now, the moment this one becomes 1, this one becomes 1 here, B will become 0, right. Now, you may say that let me first propagate this event and set this to 0, but then again when you have this change, you will again simulate this gate, right. So, if we do not follow some good ordering of the gates, then we will end up simulating the gate more than once. So, what we want to do is we want to do a topological ordering. What is a topological ordering? We want to evaluate some net when the inputs to that gate have already stabilized. So, I will evaluate B after I have evaluated this x and after I have evaluated this y. After they have been completely evaluated, then I will evaluate B. It should not be the case that I evaluate x then evaluate B using the previous value of y. No, x and y must reach their new values and only then I will evaluate B. So, it has to be ordered in some kind of level from input to output, right. So, you might say, think that okay, this is my level 1, this is my level 2 and these two are in the level 3. So, that is what we mean by levelization. Break up the gates into levels and then simulate the gates in one level before you move on to the next level, right. So, how do we do levelization? So, we execute an algorithm called topological sort. Now, many of you who are from the computer science background must have gone through topological sort, but I believe that there are a few students here who are not from computer science background. So, we will briefly go through what topological sort does. So, what we are going to do is we are going to treat these nodes, the flip flops, the gates, etc., as nodes of some graph, all right, and we are going to produce the edges in the direction in which the signals propagate, right. So, at the input side we have the inputs and the flops, because the flops, if you remember our view of the combinational of a sequential circuit, we have the combinational logic and we have the flops, right. So, we know that any sequential circuit can be drawn in this form. So, these are the flop outputs which are feeding back into the combinational logic and we have the primary input. So, as you can see that this is the logic that we want to topologically order. So, the inputs here are the outputs of the flops and the primary inputs, right. So, that is what we have here also. We have the outputs of the flops, namely Q1 and Q2, and the inputs to the combinational logic, that is in 1 and in 2. Then we have these gates also. So, we have A, and as you can see that Q1 and in 1 feeds into A, and then A fans out to B and C. So, A has fan out to B and C and so on. So, this is how we draw the graph, and the final stage will have no outputs, no outgoing edges, because they do not have anything in their fan out. Now, we will start by doing a depth first search from those nodes which have no incoming edges, right. So, we will start depth first search from there and we will start numbering the nodes in the order that they are visited by the depth first search, right. Now, every node in a depth first search has two important points. One point is when it is visited for the first time and when you are backtracking from that node for the last time, right. in a depth first search, by definition you come to the node once, you visit the entire tree that is available below that, and only then you backtrack from this node. As long as the node has any edge which has not been visited, it will first visit that node, and only when all the outgoing edges has been visited and you have come back across all of them, you will backtrace from that node. So, we are going to maintain two times for the node, the time at which it entered the node for the first time, right, and the time at which it finally backtraced from that node. All right. So, let us follow that for this graph. So, we start from this one and we start by assigning into to have 1. So, this is the time at which it enters, right, 1. From this we start the depth first. So, it will go to B. So, B gets 2, these are the entry times. Then from B we still have outgoing edges. So, let us say we first go to D. So, this gets 3. D has no outgoing edges. So, we are done with D, we should come back from D. So, we put the exit number for D as 4, that is the time when it is finally coming out from D. Then we come back to B. Now, see B still has other unvisited edges. So, it goes there. So, C is visited for the first time at time 5. So, that is the entry time for C. Then C does not have anywhere else to go. So, we can backtrack from C. So, we put the exit time of C as 6. Then we come back to B. When we come back to B, then now B does not have any more unvisited edges, both the edges have been visited. So, we can backtrace from B, and now the time is 7. Now, B is done, but where did we come to B from? From into. So, we trace back to into, backtrack to into, and in into now there is no other outgoing edges. So, it gets the exit level 8, right. Next, we again start from any other node which is not yet visited and which has in degree 0 or no incoming edges. So, let us say that we start with in 1. So, in 1 gets the entry level as 9, then from there we go to A gets the entry level of 10. From A, when we go to B, we find that B is already visited. So, no need to visit B again. When we go to C, we find that C is also visited, no need to go to C again. So, we have already covered both outgoing edges from A. So, we give it the exit level 11 and backtrack back to IN1. When we have backtracked back to IN1, then we look for the next. So, so this one now gets the exit level 12, right. Now, again we look for a node which has not been visited. So, Q1, it gets the entry level 13. Then we go to A, but A is already visited. So, we can now exit from Q1. So, it gets 14. Then we similarly go to Q2, entry level is 15. We find that D is already visited. So, exit level becomes 16 and we are done, right. So, what we have done is that for every node we have an entry level and an exit level, right. Now, what we do is that we start entering, we sort these nodes based on their exit levels. We sort these nodes based on their exit levels and process the nodes starting from the one which has the maximum exit level, right. Now, if you look at the exit labels of this, just see, this has exit label of 4, C has the exit label of 6, B has the exit label of 7, right. IN2 has the exit label of 8, A has the exit label of 11, IN1 has the exit label of 12, Q1 has the exit label of 14, and Q2 has the exit label of 16. Now, this is the sequence in which we will process the gate. So, what are we going to do? We will first evaluate Q2. So, we will make this change first, that we will change it to 0. Then we will evaluate Q1. So, we will make this one 1, right. Then we will evaluate in 1. So, this one will be made 1. Then we will evaluate in 2. Sorry, we can evaluate A, right, because in 1 and Q1 both are evaluated. So, we evaluate A and put this as 1. Then as per this we evaluate in 2. So, this becomes 1. Then we will evaluate B. So, this becomes 0, right. Then we will evaluate C. So, this becomes 1. Then we evaluate D, which becomes what will it become? This is 0, this is 0. So, becomes 0. All right. Now, can you tell me that why the exit labels gives us the topological order? This is something which we have to understand. So, this is mechanically we have done it. We just did a depth first traversal, noted down the entry times and the exit times, sorted them by the exit times, and said that this is the order in which the descending order of the exit times is the order in which we should execute them. The important thing to note here is that when we are processing a particular node, any node which is in the fan in or the cone of the fan in must already have been evaluated first, right. So, what am I trying to say? I am trying to say is that at a given point of time, if you are evaluating this node, then everything that is in the cone of this must already have been evaluated, right. Now, so we want to make sure that all the nodes that are in the fan in of this will have exit label more than this node, right. It will have exit label more than this. Now, is it possible that there is some node here, there is some node out here which got an exit label less than this? Why not? Because if this got an exit label, let us say x, then see it, when does it exit? After it has visited all the outgoing edges. So, from here again, suppose this is another node. So, from here again all the outgoing edges must have been visited. So, all the nodes in this path must have been visited, right, and then this one also was visited, and without exiting from this it cannot exit from this. So, therefore, it can never be possible that some node which is in the transitive fan in of this node gets an exit label which is smaller than the exit label of this, right. So, this establishes that when we are evaluating a particular node, if we have evaluated all the nodes which have exit labels more than this, then it has covered all the nodes that are in its transitive fan in. So, therefore, it is a good enough point of time to simulate this case. Clear? this is the algorithm pseudocode. So, we maintain a queue of ordered nodes called list. We initialize n to 1, and then this is the topological sort algorithm, which simply looks for nodes in V which is not marked visited, and then it visits V. All right. Now, you see here, when we look for node V which is not marked visited, we are not necessarily looking for nodes which have a in degree 0. We are not necessarily doing that. So, in the previous case also, you could have started your topological ordering from here, but still you see, if you gave it some, so if you started its topological order from here, then the input level of this would have been 1, the output level would have been 1, rather 2, exit level would have been 2, right. But then when you would start labeling something on the left side of this, they will anyway get exit level more than this. So, there is no harm in doing that, right. So, it is not necessary that you have to always start from the nodes which are here, you could start from anywhere and do that number, right. So, that is why we just look for node V which is not marked visited and do the recursive, we call this recursive function V. So, what does the visit function do? It first marks V as visited, which is the standard thing that we do in depth first traversal. First mark the node visited, and then we give the entry label of that node as the current value of the time. So, n is the time, is the stamp that we are using, and every time we give the stamp, we increment the stamp. Then for each u in the fan out of V, if u is not marked visited, then visit u, visit that node, and then when you have already completed the fan out of all the nodes, all the outgoing edges from V, then you should backtrack from V. So, you put V dot exit equal to n. Remember that n is a global variable. So, the value of n here and the value of n here are different, because this recursive call may have updated n several times. So, this can be a larger value of n, and then you do again n equal to n plus 1, and you insert u in front of list, because this is the order in which the exit we are, you remember that we are going to order them in terms of their exit values, and so we just add this in the front of the list, right. So, we add it in the front of the list. Why? Because the numbers are increasing and we want to finally start evaluating them from the largest exit number. So, that is why we keep on entering them into the front of the list. Finally, when we are done, then the front of the list has the largest exit number, right. Clear? Any questions about this? Right. So, then we are at the end of this lecture, and in the next lecture we are going to look at some other aspects of cycle based simulations.